Welcome everybody. Today we are presenting Graphing for Science Linear Relations. We performed an experiment where we found the volumes and mass of 6 marbles. Our task is to determine what the relationship is between the mass and volume of these marbles. The first thing we want to do is organize our data. One way to do it is to use a table. In our experiment, the independent variable is volume, which we measured in cubic centimeters, and the dependent variable is mass, measured in grams. Remember, the independent variable is what is manipulated. The dependent variable is what results come from that manipulation. Now that we have the table labeled volume, mass, volume is in cubic centimeters, mass is in grams, let's fill in the table with the data that we found. And here we have our results for our 6 marbles. Okay, now that we have found our table, the next thing that we want to do is to represent the same data in a graph. We can transfer the info that we have in the table to a graph. First, what we need to do is identify our axes. Remember that volume is the independent variable, so it goes on the horizontal axis, and the unit of measure there is cubic centimeters. The mass is the dependent variable, and it's on the vertical axis. It's measured in grams. We need to give a name to our graph so that we know what it is that we're comparing. It doesn't have to be a fancy name, but it does need to be specific enough for someone using the graph to know what is represented. So we're going to call it mass versus volume of marbles. Can't get much simpler than that. If you use a name like this to name your graph, make sure that the dependent variable is mentioned first, mass versus volume, and that means that your experiment is based on mass as a function of volume. The next thing we want to do is determine a scale to use for each one of our axes. Your scale should be large enough to fill the graph without running out of room, but not so small that it doesn't fill the graph. The horizontal and vertical axes can have, they can have different scales. They don't have to have the same scale. Designing an appropriate scale is as much an art as it is a science, but there are a few pointers. So let's go back and take a look at our table again to see what our data is. If you take a look at this data and you just think about what it is that we're graphing, we do want to include the origin in this graph. We can reason that because if an object has no volume, it has no mass, so 0, 0 will be on the graph. The horizontal goes from 0, the horizontal goes from 0 to 5, and the vertical looks like it goes from 0 to 50. So that's going to be our first consideration to decide what our axes are going to look like. So let's do the horizontal scale from 1 to 5 and just do every other one of our little tick marks, so that each one of the little tick marks on the graph represents a half or 0.5. And the same thing with the vertical. We can go from 0 to 50 in increments of 10 using every 2 little tick marks. And this will spread our graph out so that we can read it. Now let's plot the points. When you plot the points, on the graph, and then after you do that, circle them. Now the reason that we're going to circle them is, first of all, so they won't disappear when we try to draw a regression line or line of best fit through them, but also we want to represent that they are not exact, that there's a certain inaccuracy to each one of those points. Now if you draw the line of best fit, which is the regression line, through those points, or fitting them to those points as best you can, and remember, you're going to have some points that will be above the line and some will be below the line. And you just have to kind of eyeball it. You know that it's going to go through 0 or very close to 0, and then see how best you can fit it. This is not going to be exact, and that's okay. Okay, the next thing that we want to do is write the equation of the line by looking at the graph. And we're going to remember that we're talking about y equals mx plus b, which is a slope-intercept form of the line. And we also remember that m is the slope, which is the rate of change. It's very important to remember that just the word slope doesn't really describe what it is. It's the rate of change, which is the change of y over change in x, vertical over horizontal. And this is density. This is your mass over your volume. This number represents the density of the marbles. The slope of the line defined by the data is the density of the material, which is the marbles. B is your y-intercept, and again, since it goes through the origin, the y-intercept is going to be 0 in this case. Now let's go back once again and revisit our chart. We have the marble, we have the volume, the mass, and then the change in volume over change change in mass over change in volume. And we're going to find these slopes by using the point 0, 0 and the point that we have plotted. So when we do this, these are the values that we get. And you can see as the slope column is being filled in, these numbers are fairly close together. So we know that we probably have, we've done a fairly good job of our graphing. If we add these together and just average them, we get an average slope of 8.79. And once again, remember, that is the density. Slope equals density in this case. If we actually run a regression line, it comes up very close to this. It's like 8.7 something. So I think that we've done a pretty good job on this. You can run the same experiment using other like objects. Give it a try and see if you can determine that density. Bye now.